Hi guys, welcome to the next lecture. In the previous lecture, we spoke about modification of functions by vertically or horizontally. In the previous video, we spoke about how we can modify functions by shifting vertically or horizontally. What is the impact and what is essentially happening when the graph is shifting vertically? What is essentially happening when the graph is shifting horizontally? Today, we will talk about modifying functions by stretching them. So what do I exactly mean? How do you stretch a function? Let me throw some light on it. So suppose you have a function y equals to fx. If we know the graph of y equals to fx, we can sketch the graph of y equals to, say, b times fx. Now, what are we doing? We are multiplying the function fx by b throughout. B is a constant, and let's take b as greater than 0. When we multiply the function fx by a constant b, which is greater than 0, this will have the effect of stretching the graph in the y direction by a factor of b. For example, y equals to x square is a graph. And now I'm going to stretch it. And I'm going to look at the graph of 2 times x square. Let's see what change or what difference we get. This is how the two graphs will look like on the Cartesian plane. This, my friends, is the graph of y equals to x square. You can see what's happening here. At 2, the value is 4. So 2 comma 4 is what you get. And this is the graph of y equals to 2 times x square. So when, at 2, the value will be somewhere here. It's going to be 8, somewhere up here. Now, what has happened? Each y value is multiplied by 2. This remains unchanged, but the y values are getting multiplied by 2. So please note that x remains unchanged. Similarly, if you know the graph of y equals to x square, you can also try and visualize the graph of y equals to half of x square. Previously, we've done twice of x square. Now you can halve it. What are you doing? You are multiplying by each value of y is getting multiplied by half. In this graph, what I've done is I've taken into consideration all the 3 graphs that we were talking about. So I just said that we should now also look at the transformation y equals to half of x square. Y is equal to half of x square means each y value is getting multiplied by half. This, my friends, will be the graph for it. This is the graph for y equals to half of x square. This is the graph for y equals to x square. And this is the graph of y equals to twice of x square. So you would notice that, say, at 2, the value for this one is 4 by 2. So 2, 2 is the point. For the middle one, this is 2 comma 4. And for the interior one, it will go somewhere up here, okay? And it's gonna intersect at the point that you will get will be 2 comma 8 because it's going to be twice of 4. So keeping the x values the same, you can compare the 3 graphs. What has just happened? When we have y equals to half x square, the graph stretched towards the outer side. When we have y equals to twice of x square, the graph has shrunk towards the interior. Why? Because you have steeper values. You have bigger values. So you have steeper graph, okay? That's what is happening here. That's what we mean by stretching of a graph. Next, let's talk about modifying functions by reflections. So what do we exactly mean by this? You can modify a given function. Suppose you know y is equal to f of x. You can find the reflection graphically of this function in the x-axis and also in the y-axis. So let's first talk about reflection in the x-axis. When we are talking of reflection in the x-axis, it essentially means that if we know the graph of y equals to f of x, then we can sketch the graph of y equals to minus of fx. And as we will do it, the result is a reflection in the x-axis, as if the x-axis works like a mirror and you see the reflection. I think it would be clearer to you in case I take up an example. So let me take up an example. Suppose we have y equals to modulus of x. We all know what is the graph for y equals to modulus of x. Let's just put it up here. So modulus x graph would move something of this sort. X and y values. If x is minus 2, y is 2. If x is minus 1, y is 1. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2 again. So it moves something of this sort here. And similarly, it's going to move here. Okay. So V shape is the graph for modulus of x. Now, what will be the graph for minus fx? When we are talking of reflection, what in the x-axis, we are talking about y is equal to minus fx. So, which means in our example, this time y will be equal to minus of modulus of x. Minus of modulus of x would essentially mean that modulus of x is equal to x when x is greater than or equal to 0 and minus x when x is less than 0. Now, minus of modulus of x will become minus x when x is greater than or equal to 0, and it's going to be x when x is less than 0. So what does it mean? It means that, let me again give the same values. So x and y, and let's check out the behavior. So x is minus 2, minus 1, 0, 1, 2. When x is minus 2, that is x is less than 0, x comes out. So that means minus 2 comes out. When x is minus 1, that is a negative number, x comes out, that means minus 1 comes out. When x is 0, 0 comes out. When x is 1, it's a positive number. So minus of that number comes out, that means minus 1 comes out. When x is 2, minus of 2 comes out because it falls in this category and you have minus of x coming out. Okay, so this means my output is just negative. Since my output is just negative, I'm going to create a graph where I'm putting x-axis here in the top and say this is your y-axis. Now, what do you have? I'm going to put the values here. So 0 here, 1 here for x, 2 here for x, 3 here for x, so on and so forth. Minus 1, minus 2, minus 3, so on and so forth. Now, at 0, the value is 0. At minus 1, the value is minus 1. That is, it's going to be here because this is minus 1, For y, -2, -3, so on and so forth. For -2, -2. When x is -2, y is also -2. When x is -3, y is also -3. When x is 1, y is again -1. When x is 2, y is again -2. When x is 3, y is -3, so on and so forth. So your graph will be something of this sort, moving down like this. And let me show you both the graphs together. If you would try to see it, this was V and this is inverted V. This is x-axis, and it seems like x-axis is actually working like a mirror. And what we are attaining as minus of modulus of x in the graph, what you can see is the reflection of mod x, nothing else. So it's like a mirror image. And what is the mirror? The x-axis. So if we know the graph of y equals to fx, then we can sketch the graph of y equals to minus of x, and this graph will work like a mirror image of fx. The minus sign in the front has the effect of reflecting the whole graph in the x-axis. Just like x-axis is a mirror, and you get a graph which is an absolute mirror image of f of x. Just like we can find reflection in the x-axis, we can also find reflection in the y-axis. Now, how will that be possible? Let's figure it out. So here, if we know the graph of y equals to fx, if we know the graph of y equals to fx, we can actually generate a graph of y equals to f of minus x. Then we can sketch the graph of y equals to f of minus x. And when you would be doing that, you will get reflection in the y-axis. Let's take up an example to understand this situation as well. Let's understand it using an example. So I am taking the example of y equals to e to the power x. The graph of e to the power x looks something of this sort. Y equals to e to the power x. You can see that e to the power 0 is equal to 1. So at 0, you will find the graph to be here, and it moves like this, goes up. Okay, it's a convex function. Now, if you would want to see the reflection in the y-axis, what do we have to do? We have to look at y equals to f of minus x. That would mean that we are interested in the graph of e to the power minus x. Your input is minus x. For every x that you are taking up, the input turns into minus x instead of just x. So e to the power minus x. And the graph will look like this. At 0, again, when x is 0, you will get 1. So it's going to intersect the y-axis at 1 again. It's going to move exactly, if you see, the opposite direction in exact same pattern. If you want to see both of them together, this is what it will look like. This is the graph of y equals to e to the power x, and this is the graph of y equals to e to the power minus x. They're intersecting at 1 because e to the power 0 in both the cases will give you 1. So intersecting here at y equals to 1, x equals to 0. So this is the reflection in the y-axis. Let me give you another example with a graph. This is a graph of y equals to 3 to the power x. This is y equals to 3 to the power x, and this is the graph of y equals to 3 to the power minus x, because that is what we are interested in as far as the reflection in the y-axis is concerned. So what have we done today? In the previous video and including today's video, what we have done, we've done the modification of function graphically. We've done the vertical shift, the horizontal shift, what it is all about, what it takes to get those shifts. Then we worked today on two aspects. One was by stretching how we can modify the function. And the second concept is by seeing the reflection on the x in the x-axis and reflection in the y-axis.